Yeah, good afternoon. Welcome to the session. So, in this session, I will be discussing about MOSFET switch. So, before that, what is the difference between JFET and field effect transistor, that is FET? So, generally, JFET is a current controlled device, and when come to the FET, it is a voltage controlled device. So, with this, we are going to discuss about metal oxide silicon controlled field effect transistor, working principle and operation, and also construction of the MOSFET device. So generally MOSFET device characteristics are similar to JFET and additional characteristics that make them very useful. So there are two types of MOSFETs we have. So one is depletion mode MOSFET, that may be called as DMOSFET, and this DMOSFET can be operated in two modes. That is, one is with depletion mode of operation similar to the JFET. The condition is VGS is less than or equal to V0. So by the time the DMOSFET is operates in depletion mode only, so that is less than 0. And the same way the DMOSFET can be operated in enhancement mode. So when the VGS gate to source voltage is greater than 0. So this is one of the type of MOSFET. So another type of MOSFET is enhancement MOSFET. Enhancement mode MOSFET, that is you can call it as E-MOSFET. So this can be operated in enhancement mode only. So the condition is whenever gate to source voltage is greater than the threshold voltage applied. So where until the IDSS is equal to 0, there is no operation of the enhancement mode. So whenever there is a VGS greater than VT, then IDSS increases from 0 to some extent. So then it will be operated in enhancement mode of operation. So next thing is what is the basic definition between the difference between the depletion mode and enhancement mode. So the depletion mode PN channel has the highest conductivity when there is no voltage at the gate terminals. So that means P channel and N channels having the high conductivity, and the channel conductivity diminishes when the voltage across gate terminal is either positive or negative, depends on the voltage applied between the gate to source. So the channel can be changed, that is conversion of P to En or N to P. Similarly, the enhancement mode is nothing but the circuit does not work if there is no voltage across the gate terminals. So that means, so gate signal is mandatory to work the MOSFET in enhancement mode. So when the maximum voltage is applied across the gate terminal, so the device conductivity improves. So these two are the statement from depletion mode and enhanced mode of operation. So move on to the representation of DMOSFET symbols. So this will shows the N channel, and this will show the P channel. So we will discuss what is the difference between N channel and P channel. So the direction indicates that your N channel and P channel representation of DMOSFET. Okay. So the MOSFET having the three switches, gate, drain, source. So based on the direction of current flows from drain to source or source to drain, so that deep MOSFET or MOSFET can be classified into N channel MOSFET and P channel MOSFET in both the D MOSFET and E MOSFET. So when come to the working principle of MOSFET, so here the main working principle of a MOSFET device is to be control the current flow and voltage between the drain and source terminals. So that's what we are going to change the voltage or current values, or we are going to control the current between the drain to source and source to drain. So then the operation of the MOSFET will be takes place. So it works almost like a switch. A MOSFET's operation is dependent upon a MOS capacitor. So the MOS capacitor is the heart of the MOSFET. That is metal oxide silicon capacitor is the heart of the FET MOSFET. So what are the important points in the working of MOSFET? So we will see that. So the semiconductor surface which is located between the source and the drain terminal below the oxide layer, that is silicon dioxide layer, can be inverted from N type to P type by the application of either negative voltage or positive gate voltages respectively. So that depends on the applied voltage between the drain to source terminals. So the type of N type or P type can be inverted. So next one is the hole presents beneath the oxide layer are pushed downwards with the substrate when a repulsive force is applied for positive gate voltage. So this is one more statement in the construction point of view. Next one is the depletion region is populated by bound negative charges associated with the acceptor atoms. So by applying the negative voltages or bounding of negative charges at the depletion layer associated with the acceptor atoms, so there will be a layer formed at the junctions. Now a channel is developed when electrons are reached. Therefore electrons are also attracted to the positive voltage from the N plus source and drained into the channel by that voltage. So this is accumulation of electrons at the junctions by applying the positive voltage at the source to drain, then it will form a junction. So as a result, if a voltage is applied between the drain and source, current flows freely between them. So and the gate voltage controls the flow of electrons. So this is happening inside the MOSFET device. So if you apply negative voltage, a whole channel will form under the oxide layer instead of the positive voltage. So this is about when applied the negative voltage and when applied the positive voltage, the channel will be formed at the oxide layer is different. So this is the representation of construction point of depletion mode of operation of MOSFET. So in this we can observe that there are three metal connectors like gate, source and drain. So in this N is nothing but N plus highly doped two types of regions are taken, then these two are connected with the N channel. So and attached with the P substrate. So that will be represented by the SS. Substrate is the metal connector represented with the SS. So therefore the drain and source leads connect to the N-doped regions, and these N-doped regions are connected via N channel. So this will represents the N channel, and this N channel is connected to the gate via a thin insulating oxide layer. So in between this N channel and the gate terminals, there is a silicon dioxide layer connected. So the N channel N plus doped material lies on a P doped substrate that may have additional terminal connection called SS. So this one is additional connection taken because of the P substrate connected to the N doped channels, N doped regions through the N channel. So this is about depletion mode of MOSFET construction having three terminals, gate, drain, source and additional substrate called SS. So what are the regions in MOSFET? So the MOSFET can be operated in three regions. One is cutoff region. So the cutoff region is a region where no conduction occurs, and so as the MOSFET is turned off and MOSFET functions like an open switch in this situation. So whenever there is no conduction between drain to source or source to drain, that will be in cutoff region, and that situation can be called as open switch or off state of the switch. So next one is the region of ohmic. The ohmic region is defined as the region where the current IDS rises as the value of VDS rises. So that's what as we increase the drain to source voltage, the drain to source current will be also increased. So increase of drain to source voltage will result in increase of drain to source voltage. So MOSFETs are used as amplifier when they are designed to function in this range. So whenever the MOSFET is working in the ohmic region or active region, you can say, then it will be taken as an amplifier. The function is taken as an amplifier. So another region is nothing but region of saturation. So the MOSFET can be operated in saturation. The result is the current IDS is constant, remains constant despite an increase in VDS, drain to source voltage, in the saturation region. So therefore you will get the constant IDS values even though there is a change in the VDS. So which occurs when VDS reaches the pinch off voltage, that is VP. So once the threshold voltage or pinch off voltage reaches by this VDS, so then the current going to be saturated. So in this case the device will operate as a closed switch and allowing a saturated value of IDS to pass through it. So as a result, whenever MOSFETs are required to perform switching operation, this operating area is picked up. So that means, so whenever we require to operate the MOSFET as a switch, we go with the saturation region. So next, the basic operation gives the two types of characteristics in this deep MOSFET, that is depletion mode of operation or enhanced mode of operation. So that depends like, so this P is the pinch off voltage represented here. So this is nothing but depletion mode of operation. That means our VGS is less than 0, gate to source voltage is less than 0. So then therefore it is, so less than 0, therefore it is operated in depletion mode. The condition is whenever VGS is less than 0, then it will be in the depletion mode of operation. So up to IDSS 0, it will be in depletion region. So as we increase the gate to source voltage, so gradually the IDSS also increases to some extent, that is turned becomes a enhancement mode of operation of the MOSFET. So that depends on the VGS value. So if VGS is changed to, if VGS is changed to greater than or equal to 0 or greater than 0, then your IDS will be increases gradually from negative to positive flow of current. So therefore then it will be comes into conduction state of the switch. So then the corresponding output characteristics indicates that at VGS is equal to minus 5 and minus 6 or up to 0, we are going to operate in the depletion mode of operation, though there is a cutoff region and active region and saturation region, but still it is in a depletion mode of operation. So that's why it's a D MOSFET. But D MOSFET can be operated in both the areas like D and E, enhancement and depletion mode of operation. So that is nothing but the point at which IDS increases gradually from 0 to some value as increase in VGS, then it will becomes a enhancement mode of operation of the MOSFET switch. So you can observe here the transfer characteristics are similar to the JFET. So in depletion mode of operation, when VGS is equal to 0, IDS is equal to IDSS. So that means it will be IDSS only. So IDSS also at 0. So when VGS is 0. Then when VGS less than 0, that means you are going to towards a negative value, then your IDS is also towards negative, that means in the negative region only. So that is in the depletion region only. So whenever there is a change in VGS that is greater than 0, IDS changes to 0 to some positive value. So this is about depletion region and enhancement region of the D MOSFET, and the formula can be used for getting the ID value is nothing but IDSS into 1 minus VGS by VP whole square. So this is the formula to get the drain current in the MOSFET. So we'll move on to the same characteristics we can observe here, depletion mode and enhancement mode. And in case of enhancement mode of operation, the transistor operates with VGS greater than 0 volts and ID increases above IDSS. So that is Shockley equation. So the formula used to plot the transfer curve still applies, but VGS is positive. So this formula can be used for both the condition for depletion mode of operation and enhancement mode of operation, but the voltage applied is different. So in enhancement mode of operation, completely positive voltage may be applied to the device. So next move on to the p channel depletion MOSFET. So this will be operated completely from positive to negative, so that therefore the direction of current is changes. So initially it is drain to source, now it is source to drain. So here you can observe the transfer characteristics. The p channel depletion mode MOSFET is similar to the n channel except the voltage polarity and the current direction reversed. So initially it is in the opposite direction when we see here. So when we see here in the n channel D MOSFET symbols, it will be seen that the direction of current in the n channel is from source to drain, but in case of p channel it is drain to source. So in the opposite direction. So here also we can see the transfer characteristics of the D channel depletion MOSFET. So similar characteristics we may get, but the thing is the polarity of the voltage changes. Therefore, it will start with the pinch of voltage in the positive direction. We are increasing the voltage. We are applying the voltage VGS in the positive direction. Then from 0, IDS at VGS is equal to 0. IDS is some at 0 point. And as we increase the voltage, it will come to the as we increase the VGS value, VGS voltage between the gate and source, so we can observe the current value IDSS. So it is in the enhancement mode. That means it is from the depletion mode to enhancement mode. So it will come to depletion mode to enhancement mode. So it will be completely operated in positive only. So therefore, so at pinch of voltage, it is cutoff region at 5 volts. No, it is this is the pinch of voltage, the saturation region, the ground one is cutoff region, and this is the active region here. This is the active region or ohmic region. Then it will be turned into. So at VGS is equal to 0, your IDS is also 0. If you increase the VGS more than 0, that is in the reverse direction, so your current is also coming to, as VGS increases 0, at maximum value of pinch off voltage your current is ID is going to be 0 in the positive direction. So similarly we can see this output characteristics of the P channel MOSFET. So these are the output characteristics of P channel MOSFET. So the difference is between the D channel, D type of depletion mode of operation and enhancement mode of operation is nothing but, so here also there are three terminals, drain, gate and source. The construction is quite different when compared to the D MOSFET. So in the E MOSFET there is elimination of channel, so there is no channel here. So here there is no channel between the two N-type regions, but a P substrate is directly connected to the silicon dioxide layer, and silicon dioxide layer again gate terminal is connected here. So the P substrate SS can be directly connected without any channels between the two N types of regions. So this is the nothing but channel elimination. So the drain and source connect to the N-doped regions. These N-doped regions are not connected via N channel without an external voltage. So we are not applying any external voltage between the gate and drain. So the the gate connects the p-doped substrate via a thin insulating layer of silicon dioxide. So that N-doped material lies on p-doped substrate and that have an additional terminal conduction called SS. So this is similar to the D MOSFET except the elimination of your N channel between the two N type of regions. So this is the representation of E MOSFET N channel. So current from source to drain. So here also we can see the transfer characteristics of the E MOSFET. So in the enhancement mode of operation of MOSFET, so that completely operates in the positive region. So that means, so from 0 to some threshold voltage, there is no current flow of ID value. So as we increase the voltage VGS, beyond the threshold value, that is 2 volts, the IDS starts flowing through the device. Then it reaches to maximum value at some value of VGS. So this is about gradual increment of drain to source current or source to drain current as increasing the VGS. So the corresponding output characteristics also we can observe here. This is also similar to our D MOSFET. So here it is having three regions like cutoff region, ohmic region and saturation region. So as we increase the VDS value at constant VGS, so we can have the increase in the current ID. So we can have the increase in the current ID. So and get into the saturation. So that is, so we are keeping drain to source voltage constant for different values. Then we are observing the drain current while applying VDS variable. So at constant VGS applied, VDS changes and the corresponding IDS also changes in this operation of enhancement mode of MOSFET. So VGS is always positive. So that's what I said earlier. The VGS is always positive, and IDSS is 0 when VGS is less than VT. So that means from 0 to 2 volts there is no current flow. Then after pinch off voltage or threshold voltage, then it start increasing. As VGS increases above VT, ID increases. So as we see in the transfer characteristics. So if VG kept constant and VDS is increased, then ID also saturates. So that ID or IDSS is, so this indicates that, so by keeping VGS, VDS can be changed, then our characteristics will be showing that saturation region and cutoff region and ohmic regions in the output characteristics. So the saturation level VD short is reached. So this is about transfer characteristics and output characteristics of enhancement mode of operation of a MOSFET. So this is again how to calculate the value of ID in this case. So this is similar to the previous case. So ID is nothing but K into VGS minus VT whole square. So where K is the constant given by the charts, that is indicated by ID by VGS minus VT whole square. So by taking this K value, constant value from the charts, we can calculate this ID value. So this is about representation of transfer and output characteristics for enhancement MOSFET. So in this enhancement MOSFET, again the P channel is represented where the MOSFET is operated in the reverse direction, that is the voltage polarities are changes. So previously it was applied in the forward direction, now it is in the reverse direction. So voltage is applied in the reverse direction, that means reverse flow of current. So as VGS increases below the zero value, that is minus 1 to minus 6, so there also the same characteristics will be appeared similar to the N channel, but the region is negative region here in this case. Second quadrant it will be operated, but what is the difference here? You can see all the three terminals and additional SS terminal, but here we can see the 2p type of regions, highly doped regions, and one N substrate is present in this case. So and elimination of this P channel also. So this is about similar to N channel enhancement MOSFET mode of operation, and the region is where the current increases in the gradual increases in the device as VGS increases and ID also increases in the negative direction, the second region. Similarly, we can observe the output characteristics at VGS constant values, and as VDS increases, the current increases in the gradual increases to the maximum level and gets into saturation after threshold value. So this is about representation of transfer characteristics and output characteristics of the P channel enhancement MOSFET operation. So when come to the applications of MOSFET, so this can be used in many electronic circuits operation as light intensity control or motor control and max generator applications and many more applications based on this MOSFET. So MOSFET can be taken as amplifiers and widely used in radio frequency applications. So that means when it is operated in the active region, it is acts as the amplifier. So based on that operation of MOSFET, it can be used in radio frequency applications. So the MOSFET is a positive circuit component. So we can use in motor in motors to regulate the power by using these devices, or in chopper circuit like DC to DC conversion circuit as a switches, and used as a switch to operate as a analog switching devices, and auto intensity control of street light. So there are many possible ways of using this MOSFET application in all the electronic circuits. So what are the advantages from this MOSFET switch? So MOSFET switch is a high voltage controlling device, so that provides key features for circuit designers in terms of the overall performance of circuit, and some more advantages of MOSFET are listed here. So at lower voltages, MOSFET have a higher efficiency, and due to the lack of gate current, the input impedance is very high, resulting in a high switching speed. So this is the one more advantage. High switching speed is the one more advantage in this MOSFET. And MOSFET has low cost, fast transient response. So when we operate with the switches, there is a transient uh, factor affecting on the operation of switches. So that is also very fast response from the transients appears in the switches. So the oxide layer between the gate and channel prevents DC flow, DC flow or power consumption. So this is one more advantage to the oxide layer. And MOSFETs low power consumptions allows more components per chip surface area. So we can reduce the power consumption, and we can reduce the space of the design chip. So therefore we can use the uh, in many applications. What are the disadvantages from these MOSFET switches? So we'll discuss here. So because of their oxide layer, MOSFETs are susceptible to electrostatic charge damage. So because of charge formation or capacitance formation at the junctions, at the oxide layers, so there is a chance of damage of the device, and the MOSFETs becomes unreliable when they are overloaded. And MOSFETs requires thin oxide which increases the chances of leakage problems. Okay, so this is about one drawback with the thin layer of the oxide layer between the terminals. So and again, MOSFET is a unipolar voltage device, so we cannot operate in bidirectional, and increased process fabrication steps and complex circuit designs. So all these are the disadvantages or drawbacks of the MOSFET switches. And apart from this disadvantages, we have discussed many advantages through the session about the MOSFET and their operation and their conditions in the operation.